morning, AP Calc kids. Sorry about the bell there. I thought it already rang at John Baptist. Anyway, I just want to do another podcast for the week on differentials. Thank you, those who showed up yesterday for the Illuminate session. Hopefully that worked. I'm going to do, I guess, a problem or a sketch very similar to what's on page 236 in your book. So I have a function, f of x, kind of this curve here. And I have 2 points on my function. My first point is x, f of x, fancy way to say xy. And I'm going to add something to my x value, delta x. And I get a second point up here, x plus delta x, f of x plus delta x, a new x value and a new y value. Should be somewhat similar to the limit definition of the derivative. And so right here, I have my tangent line. It hits my curve right here and continues on. As I get farther and farther away from this point, you can see that that line represents that curve not as well. Local linearity says that, very close to that point, my line will represent the curve well. As I get farther and farther away, it won't represent it as well. So think of this as being magnified, a couple 100,000 times, and that these 2 points are actually pretty close to each other. So I move over some x amount, delta x, and I'm also going to call that dx. My y's value have changed from here to here, and so I'm going to say that my change in y is my second y value, f of x plus delta x, minus my first y value, f of x. I've drawn a little triangle here. This is my line. That's, let's say, my opposite side from trig, and that's my adjacent side. When I'm close to my point of tangency, my dy value is pretty close to my delta y value. As I get farther and farther away, my dy value and my delta y value will be two different numbers, and they won't be really close. My delta x is actually exactly equal to my dx. From here to here is delta x, but from here to here also can be dx. So if I'm looking at just my red triangle, I could say that my slope is dy over dx. That side over that side, rise over run. Once again, when this point, or my second point, is pretty close to my first point, I can say that my delta y is approximately equal to my dy. Here I've, for illustration purposes only, have them not so close to each other. And so I'm going to define a differential as my dy value is equal to my slope times dx. dy dx has always been my rate of change. I could also call it my slope. Okay? And so I'm going to say that my my dy is equal to my f prime of x, my slope, times dx. I'm going to call that a differential. One of the big debates in the calculus world is using dy dx. Is that really a fraction? Is it just nomenclature? And the reality is, for us, it's really not that important. Some people define this as a quotient of differentials, that divided by that. Other people say, no, it's just notation, and it's not really a fraction. For our purposes, it really doesn't matter. What's important, though, is I'm going to come back to this later in the year. And later in the year, when we have a derivative, something like that, I'm going to try and multiply both sides by dx and separate my y's and x's. And that's sort of the big point behind this. So differentials will not be something you really tested on, not super important. If you're okay with this and this graph kind of makes some sense, I'm pretty happy with that. So I hope this makes sense, hope this records okay. Thanks for yesterday's session, and I'm sure I'll be talking to you guys before the holiday. Thanks.